Okay, let's start 7.7 complex numbers. And let's take a really quick review on our number system. So far we've only been dealing with real numbers. And real numbers are made up of two sets, the rational numbers and the irrational numbers. And these two are completely different sets. If I take their intersection, there isn't anything in the intersection. No irrational number is a rational number, and no rational number is an irrational number. However, rational numbers are divided into natural numbers. That's the counting numbers 1, 2, 3, 4. The whole numbers, I add 0 to the natural numbers, 0, 1, 2, 3, 4. The integers, I add the negative natural numbers to the whole. So minus 3, minus 2, minus 1, 0, 1, 2, 3. Then the rational numbers are fractions whose numerators and denominators are integers. And of course, the denominator can't be equal to 0. And then we have irrational numbers, which are numbers like, for example, the square root of 2, or the constant pi, or the square root of 5, or really the square root of any number that's not a perfect square. If I add all of these numbers into one big set, I get the real numbers. For example, if I have x squared minus 0, an equation, is equal to 2, then x squared is equal to 2. So x is equal to plus or minus the square root of 2. So right here is a solution to this polynomial equation. I have the square root of 2. And then clearly, if the square root of 2 is irrational, so is the square root of minus 2. But as it turns out, we want a bigger set of numbers. And indeed, we either invent them or we discover them. That's a philosophical question that we don't deal with in this class. But we add to our sets to the real numbers a bigger set, and we add to it what are called complex numbers. Look at x squared plus 1 is equal to 0. Let's try to solve for x. If we do, that implies x squared is equal to minus 1. And we know that there is no real number solution to that equation. So what mathematicians did is they say, okay, presto magic, let's create one. And let's call it a solution, so it's going to be a constant. And let's call the solution I. So I is going to have the property such that I squared by definition is equal to minus 1. I put the two little dots there because by definition that is what I square is. So we defined this new solution to x squared plus 1 is equal to 0, and we called it I, and it has the property that I squared is equal to minus 1. And this I is called the, not I squared, but I. Let's go ahead and follow this out. This implies that the square root of I squared is going to be equal to I. But what is I squared? I squared by definition is minus 1. So another way to think about that is that I is equal to the square root of minus 1. So the solution is called the imaginary unit, and that's equal to I. So let's read what I have in the notes. So a complex number is a number written as the sum of a real number A and a multiple b of the imaginary unit I. And the imaginary unit I has the property such that I squared is equal to minus 1. So it's a solution to the equation x squared plus 1 is equal to 0. And for this reason, it's sometimes referred to the principal square root of 1. So another way to think about I is that I is equal to the square root of minus 1. And I is the imaginary unit. I is not a real number. But when I throw I into the pot, I can write a whole bunch of numbers this way, is A plus BI. So let's look at some examples here. So here are some examples. 7 minus 2I and 7 plus 20I. Now I want to show all of these are part of our new expanded number system. Or if you want to think about that as just set of numbers. In other words, this is a real number. This is a multiple of the I is not real. Just a reminder, is not a real number. So 2 times, or minus 2 times I, is not a real number. But our expanded number system are numbers of the form A plus BI. So 7 is equal to 7 plus 0I. So it's a complex number. Minus 2I is equal to 0 minus 2 times I. So it's a complex number. And this is already written in the form of A plus BI. So it turns out that every real number is a complex number. And when we have A plus BI, the A is called the real part, and the BI is called the imaginary. So real numbers are complex numbers, with the imaginary part equal to 0. Where 7 is a real number, but 7 is equal to 7 plus 0 times I. Minus 2I is a purely imaginary number, and the real part is 0, because that's A plus BI. And the A is 0 and the B is minus 2. At any rate, let's go ahead and it's toward the end of the semester, and you'll get some more of this when you get into college algebra. All of this will be reviewed. So let's write the following. Let's just do some exercises. We're going to write the following in I notation. So first thing I want to just remind you that nothing has really changed in our universe. All we've done is we've added some ingredients. The same ingredients before and the same things we said before are still true. Minus 36 is still not a real number. This is a purely imaginary number. And here's going to be how we're going to convert. So if A is a positive real number, then minus A is negative, and that's equal to A times minus 1. But remember, minus 1 is I squared, so that becomes the square root of A times I squared, which is the square root of A times I. So that's how we're going to write square roots in their products. And this is the real part. The square root of A is going to be real. and I is the complex unit. So that should say, there's two addendums here. That should say the complex unit I, not the complex unit I squared. I'll make the change and upload it. And I should stipulate that A is greater than 0. But I told you verbally, and that will work until I upload it and make the changes. So this is equal to the square root of 36 times minus 1. But we're using the fact that I squared is equal to minus 1 by definition. So that's equal to the square root of 36 times I squared, which is equal to the square root of 36 times the square root of I squared. And the square root of 36 is 6, and the square root of I squared is I. So that's all of the procedure you can do. But for now on, we can just simply say, if A is greater than 0, then, this is a theorem, the square root of minus A is equal to the square root of A times I. Make sure that I is out here on its own. It's not underneath the square root. So let's use that theorem. I'll add that theorem to the notes up there. I'll actually make that more explicit. So let's do number B. Using that rule, B, again, the square root of minus 5 is not a real number. But by what I just said, it's the square root of 5 times I. So here is the deal. Sometimes you will see that is written as I times the square root of 5, and sometimes you will have it written as the square root of 5 times I. I prefer this because when we look at A plus BI, B is a real number. So in this case, the square root of 5 times I is 0 plus the square root of 5i. Now the reason the book probably will prefer you to do this is because students will get lazy and write the square root of 5, and the I will stay underneath of the radical, and that's wrong. The square root of 5, if they're really careful about it, just put it in parentheses, and I has to be on the outside. Because I cannot be underneath the radical. It has to be the outside. As a matter of fact, this class does not develop the techniques to even look at what the square root of I is. You don't get that until you take a class called complex analysis, which you'd never take unless you were a math major. So let's do number C. Minus the square root of minus 20. So let's put some parentheses in here to make this easier. So that's equal to minus the square root of 20 times I, which is equal to minus the square root of 20 times I. So that's pretty simple, writing numbers with I notation. So here in the next, we have to be really, really careful. Because earlier we had a theorem. And this is the reason theorems are really, really important. We said if the square root of A and the square root of B, this is the literal theorem, if the square root of A and the square root of B are real numbers, that means their imaginary part is 0, then the square root of A times the square root of B is equal to the square root of AB. So here's what I want to tell you. if A and B are less than 0, then the square root of A and the square root of B are not real numbers. So that rule does not apply. So does not apply. It only applies if they are. So they're not, and we're going to do these ignoring that rule. And we're going to do them the exact same way that we've been doing them. So, example. A. The square root of 3 minus 3 times the square root of minus 5. Well, that's equal to the square root of 3 times I times the square root of 5 times I, which is equal to the square root of 3 times the square root of 5 times I squared. Recall, I squared is equal to minus 1. That should be your mantra. So this is equal to minus 1 times the square root of 3 times the square root of 5. Now both 3 and 5, it's supposed to be 0 there, are greater than 0. So I can use the rule that I was just talking about. So that's minus the square root of 3 times 5, which is minus the square root of 15. So with that in mind, let's do another example. 2b. The square root of minus 36 times the square root of minus 1. Well, this is, if you want, you can put the I out in the beginning. That's I times the square root of 36. And remember, I squared is equal to minus 1, which implies I is equal to the square root of minus 1. So the square root of minus 1 is I. So that's the same as I squared. I times I is I squared, that still works, times the square root of 36. I squared is equal to minus 1 times the square root of 36 is 6. So this whole thing is equal to minus 6. Interesting properties. So let's do C. Let me write it down and then I'll give us some more room. 2C. The square root of minus 125 over the square root of 5. Well, if we want to write it with I at the beginning, that's fine. That's I times the square root of 125 over the square root of 5. But there's things we can do about simplifying the numerator, because 125 is equal to 5 cubed. Remember that list of cubes I told you to memorize? It's helpful now. So that's I times the square root of 5 cubed over the square root of 5, which is equal to I. Remember the square root has index 2, so I'm going to introduce a square. 5 cubed is 5 squared times 5, divided by the square root of 5. Get some more room over here. Well, my index is 2, so the base can come out. So it comes out from underneath the radical as 5 and multiplies times I. And all I have left, what has to remain behind, is the single factor of 5 divided by the square root of 5. And since the square root of 5 is in the numerator and the denominator, those cancel, and the end result is 5 times I. So basically, we're going to write all of our complex numbers in this form, a plus bi. And when we add complex numbers, all we do is we add the real parts and the imaginary parts. All of this rule, please do not look at this and try to memorize this formula. It is a formula, and if you're really good at memorizing it, you could. There's no reason for it. You'll see that it's really natural. So let's add together. So my first complex number is 2 plus 3i. And I'm adding minus 3 plus 2i. So what I do is, since that's a plus there, I take my real part. So the real part here is 2, and the real part over here is minus 3. So I add together the real parts, and then I add together the imaginary parts. So 2 minus 3 is minus 1, and 3i plus 2i will have 3 of something, and I add 2 of that something, and that gives me 5i. And notice that that is in the form of a plus bi. A is the real part, and indeed minus 1 is a real number, and the bi is the imaginary part. And in this case, that's 5 times I. This is a pure imaginary number. This is not a real number. So once I have I, that's my imaginary unit, I can multiply it by any real number, and I have a pure imaginary number. So 5i is not a real number. It's purely imaginary. Minus 1 is a real number, like it's always been. So let's do 3b. 5 minus 1 minus I. Well, minus, so this is the same as, so this is, if you don't know what to do right now, you should immediately see that's the same as 5 plus 1 plus I. So if you want, you can always say, I want to change this into 5 plus something. So by changing the negative to the from the minus to the plus, the price I have to pay is everything in parentheses has to change its sign. And once I get a plus, I can just remove the parentheses. This becomes, sorry, I didn't write down what I wanted to write right there. There we go. 5 minus 1 plus I. So that gives me 4 plus I as the answer. Now we'll do this last one. Minus 3 minus 7i minus 6. Well, since there is no minus in front of these parentheses, I can just remove the parentheses. But minus a minus 6 is plus 6. So I group together the real parts and the imaginary part. Minus 3 plus 6 is 3. Minus 7i. So when we have 3 minus 7i, again, 3 is the real part, minus 7i is the imaginary part. So 3 is just a plain real number, and the imaginary number is the minus 7i. Together, they make up complex numbers. So that's the reason the set is not the set of imaginary numbers. The new set that we just created is the set of complex numbers. I'm not even going to go through that. When we multiply complex numbers, it's just a mess. Just remember that I squared is equal to minus 1, and we multiply just like we've always multiplied. So multiplication, the only weird thing is division. And we'll just go through some really simple examples of division. So 7i times 3i. You'd group together like terms. 7 and 3 are real numbers. Then I multiply I times I. So 7 times 3 is 21 times I squared. But recall, I squared is equal to minus 1. So this is 21 times minus 1, which we usually write as minus 21. Three I times 2 minus I. Again, just remind yourself that I squared is equal to minus 1. So this is equal to, again, distribution. All of the properties hold. So this is equal to 2 times 3i, or 3i times 2, minus I didn't have to erase the minus. Minus 3i times I. So that's equal to 2 times 3 is 6, so that's 6i minus 3i squared. So that's 6i minus 3 times minus 1, using the fact that I squared is equal to minus 1. So this is 6i minus 3 times minus 1 is plus 3. So this is 3 plus 6i. I'm quite happy if you write it this way, but this is the traditional way. The real part comes first, and the imaginary part comes second. We have 2 minus 5i times 4 plus I. Again, we remind ourselves that I squared is equal to minus 1. So you can FOIL this or whatever, but that's 2 times 4 plus I times minus 5i times 4 plus I. Well, 2 times 4 is 8. 2 times I is plus 2i. Minus 5i times 4 is minus 20i. And minus 5i times I is minus 5i squared. So this is equal to 8. These are like terms, so I can add them. 2i minus 20i is minus 18i. And minus 5 times I squared, which is minus 1. So remember, I is a imaginary. It's a purely imaginary number. I squared is real. So this is equal to 8 minus 18i. Minus 5 times minus 1 is plus 5. So that's 8 plus 5 minus 18i, which is equal to 13 minus 18i, a plus bi, where a is equal to 13 and b is equal to minus 18. So the next one is going to be dividing complex numbers. Again, a big, huge formula. So we're just going to do 2 of these, and that's it. You'll learn how to do this more in intermediate algebra. Not intermediate, but college algebra. So here is going to be the insight. So remember when we were rationalizing denominators and I was talking about the conjugate? So let's talk about conjugates. If a plus bi is a complex number, b not equal to 0, means it's a true complex number. It's not a real number with 0 imaginary part. Then a minus bi is the conjugate of a plus bi. So let's see what happens when we multiply conjugates. Let's actually get an example. 1 plus I times 1 minus I. Well, remember the a plus b times a minus b factorization? That's equal to a squared minus b squared. We're going to use that here. Here a is equal to 1, so that's 1 squared minus I squared. So 1 squared minus I squared is equal to 1 squared minus, what is I squared, people? I squared is minus 1. So 1 squared is 1, and minus a minus 1 is plus 1. So that's actually equal to a real number. So when we divide complex numbers, we're going to be kind of doing the same thing. Instead of rationalizing the denominator, we want the denominator to be a real number. So we will do 5a. So 2 plus I over 1 minus I. So I want to multiply this by something that is equal to 1. And it turns out that if z is a complex number, then we still have that is such that z is not equal to 0, then z divided by z is still equal to 1. So if a plus bi, if at least one of the a or the b, if not both a and b are 0, if I divide them, that's still going to be equal to 1. So I want to multiply this by a choice of 1. So again, here I have my sum. So the choice I'm going to be made depends upon my denominator here. I'm going to write the conjugate of 1 minus I. So all I have to do is change the sign . So the numerator is 2 plus I times 1 plus I over 1 minus I times 1 plus I. So let's go ahead and do this. 1 minus I times 1 plus I is 1 squared minus I squared. Of course, we'll want to work on that using the fact that I squared is equal to minus 1. And up here, I'm going to FOIL. 2 plus I times 1 plus I is 2 times 1 plus 2 times I. I'm foiling it because I can write it out. I plus 1, I times 1, sorry, which is plus I, and I times I plus I squared. So that can be simplified. So the numerator is 2 plus 3I. 2I plus I is 3I, and I squared is minus 1. And down here, that's 1 minus, what is I squared? Minus 1. So all of this turns out to be, now we add the real parts. 2 minus 1 is 1. That becomes my numerator. And 1 minus a minus 1 is the same as 1 plus 1. So that's 2. Now if you want to write this in the form of a plus bi, notice this is the same as 1/2 plus 3/2 times I. So a is equal to 1/2 and b is equal to 3/2. Now I'm going to tell you a trick on number b. And if you get one of these, it'll be like number b. You'll get to do examples like number 5 when we get to college algebra 5a. I'm going to keep everything really basic because you're getting hit with an awful lot of new stuff here at the last 2 weeks. 7 over 3i. Well, notice that 3i is equal to 0 plus 3i. So the conjugate of 3i is 0 minus 3i. And if I want, I can multiply the top and the bottom by minus 3i. But notice that the minus 3's are going to cancel. So I might as well just multiply the top and the bottom times I over I. I'm being lazy here. And that's going to give me 7 times I is 7i. And 3i times I is 3i squared, which is 7i. And again, recalling I squared is equal to what? Minus 1. So that's 3 times minus 1, which is equal to 7i over minus 3. Or if you want to write it as minus 7/3 I. So minus 7/3 I is 0 minus 7/3 I. It's a purely imaginary number. The real part is equal to 0. So the real part is 0. The imaginary part is this. This is a purely imaginary number. So one last thing, powers of I. So we're going to develop something. Let's prove something that's really, really easy. And let me make sure I have this down here. Yeah, oh, I've corrected that. So our theorem is I cubed is equal to minus 1. Well, let's prove I cubed is equal to minus 1. So let's start out with I cubed. Well, I cubed is equal to, so I want to prove that I cubed, I think I misspoke earlier, is equal to minus I. That's what I want to prove. Is that what I have up there? So this should be, there's an error here. This should be I cubed is equal to minus I. Apparently I have not corrected that. So notice I cubed, that should say is equal to minus I. I will correct two things after this is over and upload it. So that's what we want to prove. So that's equal to I squared times I, but I squared is equal to minus 1. So this is equal to minus 1 times I, which is minus I. So let's look at a table of powers of I. So I is equal to I to the first. I squared, what is it equal to? Minus 1. I cubed, by my theorem, is equal to minus I. What's I to the fourth? Well, let's figure it out. I to the fourth is I squared squared. But I squared is minus 1. So minus 1 squared is 1. So, okay, so there's something. So I squared not going to write exponents. I is equal to I. Well, yeah, I guess I want to leave it up here. I to the first is equal to I squared is equal to minus 1. I cubed is equal to minus I, and I to the fourth. Well, what about I to the fifth? Well, I to the fifth is I times I to the fourth, which is I times 1. Okay. What about I to the sixth? Well, I to the sixth is I to the fifth times I. But I to the fifth is I, and I times I is I squared, which is minus 1. I to the seventh is equal to I to the sixth times I, but I to the sixth is minus 1 times I is minus I. And I to the I to the eighth is equal to I to the seventh times I, but I to the seventh is minus I times I is minus I squared, which is minus 1 times minus 1, which is 1. So let's look at the pattern. I to the fifth is equal to I to the sixth is equal to minus 1. I to the seventh is equal to minus I, and I to the eighth is equal to 1. So I have I minus 1 minus I 1, I minus 1 minus I 1, and indeed that pattern is going to repeat. So this is the table that we need to know right here. And I hope I've convinced you of the following. That the pattern repeats after every 4. Keep going down 1, 2, 3, 4, 5, 6, 7, 8, and the pattern repeats. So what we want to do is we want to find powers of I. So this is example example 6A. And what we want to do is we want to simplify powers of I. So I to the seventh. So what we do is divide the exponent, in this case 7, by 4. Its remainder will be either some number between 0 and 3. So we can say I to the 0th is equal to 1. Then use the table up here. I'll give you a new table. I to the 0th is equal to 1. I is equal to I squared is equal to minus 1, and I cubed is equal to minus I. Use this table. So let's find out what I to the 7th is equal. It's going to be I to some power, and that power is going to be reduced to something. It's going to be one of these three possibilities: 1, I, minus 1, or minus I. So let's divide 7 by 4. Well, it will go into it one time, and remainder is equal to 3. So here, that's the same as I cubed, which is equal to minus I. So let's do B. I to the 20th. Well, again, we're going to divide 20 divided by 4. Well, that goes with remainder is equal to 0. So this is the same as I to the 0th, which is equal to 1. See? I to the 46. Well, when we divide 46 divided by 4, we get a remainder of 2. So that's the same as I squared. So that's equal to minus 1. And then our last example. And this, I promise you, will not be on your exam. But I to the minus 12. Well, what we want to do is multiply it by some form of 1. But remember, I to the 0th is equal to 1. I to the 4th is also equal to 1. I to the 8th is equal to 1. I to the 12th is equal to 1. And I to the 16th is equal to 1. In other words, I to the 4 times any natural number n is equal to 1. So I'm going to multiply this times I to the 12th. I have to choose one of these powers because it has to be equal to 1. And then the familiar rule of adding exponents comes into play. So that's equal to I to the 0th power, which is equal to 1. So that was not so bad. Let's do one more example. Let's do I got it? Nope. I to the minus 17. Well, I to the 20th is equal to I to the 4 times 5, so that's equal to 1. So I'm going to multiply I to the minus 17 times 1. So that gives me I to the minus 17. And I'm going to use that. I want 20 to be larger than minus 17. in absolute value. So I to the 20th. So that's equal to I to the minus 17 plus 20. So that's equal to I cubed, which is equal to minus I by our theorem. Okay, that's it for 7.7.